In kinematics, we have learned how to describe movement of objects without thinking about why they move the way they do. In this topic, dynamics, we will try to understand why objects move in a particular way and what is actually needed to change the way they move. We will cover ideas such as momentum and force. We will also cover Newton's laws, and we'll use Newton's laws to explain how objects fall without and with a resistance. Objects around us are made of matter. The quantity of matter in the object is what we call mass. The more mass an object has, the more difficult it is to change the way it moves. We can say that objects with more mass have more inertia. A train is more difficult to accelerate or to stop compared to a car because it has more mass and more inertia. Mass is a scalar quantity, so it does not have direction. Kilogram is the base unit of mass. It is important to remember that the mass of a given object does not depend on its location. The same object has the same mass on Earth, the Moon or Mars. We can use concepts of mass and velocity to define another useful quantity called momentum. Linear momentum is defined as the product of mass and velocity. It is a vector quantity which has the same direction as the velocity of the moving mass. Momentum tells us how difficult it is to stop a given object. The more mass it has, the faster it moves, the more difficult it is going to be to stop. A train going fast is not as easy to stop as a slowly moving car. Momentum doesn't have any special units. Since it is a product of mass and velocity, it is measured in kilogram meters second to -1 or kilogram meter per second. In the world around us, objects interact with each other. These interactions can have different natures. It could be because objects are in contact and push or pull each other. It could be because of gravity, magnetism, electricity, or other reasons. To be able to discuss why objects move in a particular way, we need to be able to describe and measure the strength of those interactions. The quantity physics uses to describe strength of interactions is called force, and it is defined as the rate of change of momentum. The stronger the interaction, the bigger the force. The bigger the force, the quicker the change of momentum, which means that greater force will cause the same change of momentum in a shorter time, so bigger force can cause more rapid acceleration of a given mass. Force is a vector quantity and it has the same direction as the direction of the change of momentum, which we'll discuss later in this video. Base unit of force is kilogram meters second to -2, which was given its own name, Newton. Let's now look at how we could work out the average force using a momentum time graph. Let's assume we want to calculate the average force in the first 10 seconds. The total change of momentum in the first 10 seconds is 10 kg second to -1. Since the average force is equal to the change of momentum divided by change of time, in this case the average force in the first 10 seconds is 1 Newton. If we want to calculate the force at a specific time, let's say at exactly the 6th second, we can draw a tangent to the graph at this time. Gradient of this tangent will give us the instantaneous force, which in our case is 0.76 newtons. In this example, we will calculate the average force acting on the ball during its collision with the wall. We have a ball of mass m moving with initial velocity u towards the wall. After the collision, the ball is moving with velocity v away from the wall. Let's assume the following information was given to us. The mass of the ball is 2 kilograms, magnitude of both initial and final velocities are 5 meters per second, and the ball was in contact with the wall for 0.1 second. Force is equal to the rate of change of momentum, and change of momentum is equal to the final momentum minus the initial momentum. Velocity is a vector quantity. So before we put any numerical values into our equation, we need to consider the directions of our initial and final velocities. It is generally a good idea to pick the direction of the initial velocity as positive, so in our case we will assume that towards the right is the positive direction. Now we are ready to substitute numerical values into our equation. Note that the final velocity is negative. That's because it is in the opposite direction to the direction we chose as positive. The final result is minus 200 newtons. Since force is a vector quantity, this negative sign shows that the direction of the force exerted by the wall on the ball is towards the left. This force is responsible for slowing down, stopping, and then accelerating the ball in a negative direction. Since the velocity of the ball changes direction, its momentum also changes. Change of momentum is a consequence of the force acting on the ball. Let's look at another example of calculating change of momentum and average force. This time, initially object of mass m is moving east, and as a result of the force acting on it for 10 seconds, it changes its direction and eventually is moving south. This time we have the following information. Again, force is equal to the rate of change of momentum, and change of momentum is equal to the final momentum minus the initial momentum. Putting m in front of the bracket, we get the change in velocity. Since velocity is a vector quantity, we have to subtract the vectors to find the change of velocity. We can calculate the magnitude of the change of velocity using Pythagoras' theorem. After substituting all values we now have, we get the magnitude of the average force, which is 1.42 newtons. The resultant force has the same direction as the direction of the change of momentum, which has the same direction as the direction of the change of velocity. So in this case the direction of the average force is southwest. So far, to keep things simple, we have discussed only one force acting on an object. In reality, there are usually many forces acting on a single object, but all those forces can be replaced by just one force called the resultant force. The resultant force is a sum of all vector forces acting on the body. We can define the resultant force in the following way. All the forces acting on the body can be replaced by one single force that has the same effect as all the other forces. This single force is the resultant or net force. In all examples discussed so far in this video by force, we actually meant the resultant force. Let's look at few most common examples of resultant force calculations. In the first case, we have two forces in opposite directions acting along the same line. Taking directions of vectors into account, we can treat one of the forces as negative, so to calculate the magnitude of the resultant force, we need to subtract the magnitude of the two forces. In the second example, forces are at right angles. In a case like this, we can use Pythagoras' theorem to calculate the magnitude of the resultant force. We can rearrange the force-defining equation into this form. It is worth knowing that the product of force and time in which the force acts is called impulse. Looking at the graph of force against time, we can notice that the area under the force-time graph represents the change in momentum. This example shows this idea in practice. Notice that a part of the graph is below the time axis. In cases like this, the change of momentum represented by the area above the time axis, A1, should be treated as positive, and the change of momentum represented by the area below the time axis, A2, should be treated as negative. So total change of momentum in the first 3 seconds in this example is 1.5. Isaac Newton proposed 3 important laws describing forces and their effects on motion. Newton's first law describes a situation in which there is no external resultant force acting on a body. Using the definition of force, we can see that if there is no resultant force acting on a body, the initial and final velocities are equal. This means that if there is no resultant force, there is also no acceleration and no change in momentum. These observations allow us to formalize the Newton's first law in the following way. A body remains at rest or continues moving at constant velocity unless it is acted on by a resultant external force. Newton's second law describes a situation in which there is an external resultant force acting on a body. Once again, using the definition of force, we can find the relationship between the resultant force, mass, and acceleration. This relationship can be summarized by Newton's second law. For a body of constant mass, its acceleration is directly proportional to the net force applied to it. Acceleration and the net force are in the same direction. Newton's third law tells us that forces always come in pairs. If there is a force acting on an object, there must be another force of the same magnitude and the same type acting in the opposite direction on another object. Let's talk about a few other types of forces that you will often see in exam questions. Friction is a force that holds back the movement of sliding objects. Friction always acts in the direction opposite to the direction of motion, or if an object is pushed but does not move, friction acts in the opposite direction to the pushing force. Air resistance is another example of a frictional force. It acts on objects moving through air and is also always opposite to the velocity of the moving object. Weight is the name given to a force acting on a mass in a gravitational field. We'll come back to the concept of gravitational field in A2 part of the course. For now, you just need to know that if a mass is placed in a region close to another mass, it experiences a force called weight. Weight is a product of mass and gravitational field strength. Gravitational field strength close to the surface of Earth can be assumed to be constant and equal to 9.81 newtons per kilogram. This means that an apple with a mass of about 100 grams will be pulled towards the center of the Earth with a force of about 1 newton. The same apple on the Moon would still have the same mass, but its weight would be about 6 times smaller due to the 6 times weaker gravitational field on the Moon. Situation in which the weight of the object is the only force acting on it is called free fall. Definition of weight and Newton's second law can be used to show that the acceleration in a free fall does not depend on the mass of the object and is numerically equal to the gravitational field strength. Since weight is the only force acting on the ball, and it remains constant throughout the motion, the velocity of the ball increases at constant rate, which means the ball moves with constant acceleration. As we can see, a ball with a smaller mass accelerates at the same rate. Please remember, free fall acceleration does not depend on the mass of the object. Let's see how the same ball would fall if there was a resistance. Let's watch it again. Initially, the ball is not moving, so it does not experience air resistance. The only force acting on the ball is its weight, so the ball initially falls with free fall acceleration. As the speed of the ball increases, the air resistance acting on it also increases. Since the weight of the ball remains constant, this results in decreasing resultant force and, according to Newton's second law, decreasing acceleration. The ball still accelerates downward, but its speed increases at decreasing rate. After some time, the ball reaches speed at which the air resistance becomes equal and opposite to the weight. At this point, the resultant force is reduced to zero, and according to Newton's first law, the ball no longer accelerates, but instead it moves with constant velocity. This maximal velocity is called terminal velocity. Deployed parachute suddenly increases the air resistance. This produces upward resultant force that causes deceleration. As the ball decelerates, air resistance and upward resultant force decrease. Eventually, resultant force becomes zero again and ball reaches new, slower terminal velocity. Let's see what happens when we repeat the same experiment using a ball of the same size but lower mass. As you can see, the initial resultant force, which is just equal to the weight, is lower now, but despite that, the initial acceleration is the same as for the heavy ball. This is because both balls are initially in a free fall, and free fall acceleration does not depend on mass, as we have previously discussed. Terminal velocity of the lighter ball is now lower because less air resistance is now needed to produce zero resultant force, as weight is now less than for the heavy ball. After the parachute is deployed, the ball again decelerates, reaching new, lower terminal velocity. This video covered the most important dynamics concepts. In the next one we will look at some examples of how all this theory can be applied to solve typical exam questions. Thank you very much for watching and see you in the next Easy Physics video.